Hello everyone, welcome to the another lecture of chemical bonding class 11. So in the last class we have discussed about the molecular orbital theory, right? So now in today's class we will discuss about the formation of molecular orbital theory, okay, or not, sorry, molecular orbital diagram. So first of all we will start with the molecular orbital from s orbit, okay. So let's take psi a and psi b be the wave function of the two s orbital, okay, s orbitals. So the linear combination of these orbitals will give uh, bonding and anti-bonding molecular orbital, right? So if it will give bonding molecular orbital, just we have seen in the previous class, psi b, it will be psi a plus psi b, right? Now if it will give anti-bonding, then it will be psi a is equal to psi a minus psi b, right? So when it will give bonding, it will give this, and when it will give anti-bonding, this will give this, right? So here this psi b, this one, when we talk about this, is obtained when this plus plus means what, when crust and crust region of both s orbit overlaps along the internuclear axis, right? Means crust one s orbit, the crust of one s orbit will combine with the crust, overlap with the crust of other orbit, okay. So this psi b will form when there will be plus plus, right? When there will be a plus plus, mean crust crust region of both s orbit, s atomic orbit overlap along the internuclear axis, right? Now while the psi a, this one, when you talk about this, it will be obtained when one of plus, another one of minus, means one will be crust and another will be trough region of the atomic orbital overlap, right? Now if the combining atom, if the combining atoms orbits are suppose 1s and 1s, okay, 1s and 1s, 1s and 1s. So at that time psi b, this one will be designated as let me write here, it will be designated as sigma 1s, right? And the psi a, this one psi a, it will be designated as sigma star 1s, okay. And formation of this is sigma 1s and sigma star 1s, as we can see here, right? Let me draw here. Suppose this is our 1s and another one is 1s here, okay. These two are suppose overlapping, right? So what it will form, it will form two type, okay. It will form a two type, it will two type of atomic orbital. In one case it will be when there will be a psi a plus psi b, okay. And another case will be when there will be psi sorry, here we will take minus, okay. Here we will take minus. Suppose here is psi a minus psi b, okay. And suppose here is psi a plus psi b, okay. So at that time the two type of orbital will form, okay. The it will form like this. When we talk about this, it will form like this, okay, just touching each other. So this will be denoted as sigma star 1s, okay. And from this way they will form like this, they will form like this. This is designated as sigma 1s, okay. So I hope you have understood this. Now if the combining atom is obtained are 2s and 2s, okay, the bonding molecular orbital is represented by like this, sigma 2s, okay, or sigma star or sigma star 2s, if there is the combining atom is 2s. Okay, so this was about the formation of molecular orbital from s or s atomic orbital, right? Now I hope you have understood this, right? Now next is molecular orbital from p atomic orbital, right? So we know that the three p orbitals are directed along the three coordinates, which is x, y, and z, right? So if we are taking, if z axis is taken as a internuclear axis, okay, if we are taking z axis as pz, means if we are taking pz as a internuclear axis, that is what we can say, the line joining the center of the nuclei in a diatomic molecules. Okay, so at that time the overlap of p orbit or p orbitals can be either head on or it can be sidewise. Okay, either it will be head on like this, either it will be head on like this, or it will be sidewise like this. Okay, so you will see, if the head on overlap, that is when the overlap along the internuclear axis gives bonding and anti-bonding sigma molecular orbital, while the sideways, when we talk about the sideways overlapping, it will give 4 pi molecular orbital. Okay, we will see this. Okay, now the two molecular orbital which will be obtained by the combination of this px orbit, and while the other two are will be obtained by the combination of 2y orbit. Okay, orbits. So we will see that. So if there is an head-on overlap, okay, if there is an head-on overlap, means what? Suppose we are taking along the z-axis, so this is like this, and this is like this. Okay, if there is an head-on collision, this is along z-axis. Okay, this is along z-axis, this is along z-axis. So if there is a head-on collision, so at that time two cases will arise. Okay, one will be psi a minus psi b again, and another cases will be psi a plus psi b. Okay, so when they will when there will be psi a plus psi b, so at that time they will form anti-bonding like this. Okay, sorry, they're not, they're just touching here. Okay, like this. Okay, and when there is psi a plus psi b, at that time there will be, they will form like this. Okay, like this. This will be minus, this is minus, this is plus, and here minus, plus, here again minus, here again plus. Okay, so this is called what? Sigma star p z to sigma star 2pz. Okay, and this is called sigma 2pz. I hope you have understood this, right? Where there will be a head-on collision, at that time they will form sigma star 2pz, means anti-bonding molecular orbital here. And when there will be a, so when there will be, when the crust of one will, means why it is forming, it is forming because the crust of one is colliding with the trough of one, and this is forming why, because in this case the crust of one, the crust of the crust of one is colliding with the crust of another. That is why they are forming a bonding molecular, this is called bonding molecular orbital, and this is called what? Anti-bonding molecular orbital, right? So anti-bonding molecular orbital is formed when the crust of one will collide with the or overlap with the trough of other, and when bonding molecular orbital will form when the crust of one will overlap with the crust of another one, right? So this was about the head-on overlapping, when there will be a head-on overlapping. Okay, now when there will be a okay, up to this we have understood, right? Now what we can say, the combination of this 2pz orbit gives what? Sigma molecular orbit, right, which is 2pz and 2p, 2p sigma 2pz and sigma star 2pz, right? Because these molecular orbits are symmetrical, okay? And about the internuclear axis, these molecules are and these molecular orbitals are symmetrical about the internuclear axis, okay? And the energy, when we talk about the energy of this 2pz orbit, will be less than the combining 2pz atomic orbital, okay? While the energy of 2b 2p sigma star 2pz is higher than the combining orbital. Let me write here so that you can understand that when we talk about the energy of this sigma 2pz, okay, will be less than uh, the bonding molecular orbital, okay, atomic orbital, which is 2pz, okay, and which will be greater than sigma star 2pz, okay. So I hope you have understood. This is the variation in energy. This one will be first, after that the atomic orbital, and after that anti-bonding molecular orbital, okay. Now again, when we talk about the side wise overlapping, so if z-axis we are taking here as an internuclear axis, so it is quite obvious that the 2px and atomic orbital on the two combining atom can overlap only in a sidewise fashion, okay. That is what we can say, that they will overlap along the line perpendicular to their axis, okay. Now in this type of overlapping, when we talk about this type of overlapping, so in this type of overlapping, overlaps give what, pi molecular orbitals, because they are not symmetrical, okay. But they are not symmetrical to the internuclear axis, that is why they used to give a pi molecular orbital. Now when this 2px orbital overlap in a phase like plus plus, that means crust crust or trough trough, at that time they will form, at the time they will form what, pi star 2px. And if they are means this type of overlap, what it will do, it will give a pi molecular orbital, okay. And because they are not symmetrical, right, to the internuclear axis. But when this 2px orbital overlap in the plane like plus plus, a bonding molecular orbital which is pi 2x is obtained. And in case of 2px atomic orbital overlap out of the phase which is plus minus, at that time anti-bonding molecular orbital used to form, which is sigma pi star 2px is obtained. So we'll see it through diagrammatically. Suppose this is a z-axis, okay. There is a z-axis, so along the z-axis there is, suppose this is an x, 2px, sorry, 2 2px this is, and suppose this is 2p, 2p here also 2px, okay. So this is along here, along x, here along x, okay, x. So what will happen, they will also form two type, okay. They will also form two type when there will be a sigma psi a, when there will be psi a minus psi b, okay. And one case will be when psi a plus psi b, okay. These are the two criteria, right. So when there will be psi a minus psi b, at that time they will form like this, okay, one here, 2 3 4, okay. But when there will be psi a plus psi b, at that time they will form like this. So this is what, this plane, when you are seeing, this plane is called what, nodal plane, okay. This plane is what, this is a nodal plane here. So in this case, how many nodal plane is there? When you talk about this case, the nodal plane is 2 here, okay. But in this case, when we talk about here, nodal plane is 1, okay. So this is what, this is sigma star, oh, sorry, pi star, this is pi star 2px, and this is and this one is pi 2px. Okay, so I hope you have understood this also, right? So when we talk about the formation of this 2p, so up to this you have understood, right? So the formation of this molecules obtained from 2px is shown here, as you can see here, right? Now if we are talking about the formation of I am erasing this one. If we are talking about the formation of this pi 2p y and pi star 2p y, okay, at that time the molecular orbital the molecular orbital by the linear combination of 2py atomic orbital can be explained in a similar manner as we have already discussed here, right? Now again, when you will see in 2 pi 2px and 2py molecular orbital, the electron density is concentrated into two regions, okay, above the above and below the plane in an internuclear axis, right? Let me draw you. When we have seen the combination, one was here, another one is here, right? It is what it was, right? It was pi 2px, right? So when we are talking about the pi 2px, or if we will take here pi 2py, it will be same, right? So here we will see that the electron density is concentrated into two regions. One region is this and another region is this, right? It is concentrated into these two regions, okay, above and below the plane, and containing the internuclear axis, right? And this plane is called what? Nodal plane. This plane is what? Nodal plane, as I have already told you, right? And the electron density, what is nodal plane? As I have already discussed about this, nodal plane is the area or the place where the density of finding an electron is zero, right? So the electron density is zero in the nodal plane, right? Now when we talk about the anti-bonding molecular orbital, which is I'm erasing this one, which is pi star, which is pi star 2px, and or we can write pi star 2py, pi star 2py. At that time we have seen that the orbit possesses least electron, the orbit possesses the electron density in a internuclear region, right? Like this, in an internuclear region. And how many number of nodal plane is? Two here, right? One is here and this one, right? So this was about the formation of molecular orbital, right? Now we will discuss about the relative orbital of energy of molecular orbital, okay? We will talk about the energy of the molecular orbital. So when we talk about the energy of the molecular orbital, it will depend on some factors, okay? Some factors. So what are the factors? It will depend on the factors, that is the nature of the atomic orbital form from which it has been formed, and the next one will be the extent of overlapping between the two atomic orbital forming the molecular orbital, okay? These are the two major factors on which the energy of the molecular orbital will depend upon, okay? So we will see this. So we know that the order of the energy of the molecular orbital has been calculated on the basis of what? Ultra nuclear spectroscopy, right? And the sequence of energy of this molecular orbital for homonuclear diatomic molecules, except oxygen and fluorine, O2 and F2 molecule, will follow this order, okay? The sequence of energy of the molecular orbital for homonuclear diatomic molecules except O2 and F2 molecules will follow this order. The order will be, first will be sigma 1s, after that sigma star 1s, okay, after that sigma 2s, after that sigma star 2s, okay, after that here pi 2px and pi 2py, after that sigma 2pz, okay, after that sigma 2pz, and after that again sigma star 2px, and pi star 2py, pi star 2py. Okay, and after that at last it will be sigma star 2pz. Okay, so the sequence of energy of a molecular orbital for homonuclear diatomic molecules except oxygen and fluorine, O2 and F2, will follow this sequence. Okay, now next is, in case of, if we are taking the case as we have just what excluded O2 and F2, right? So now in case of O2 and F2 molecules, the energy of this sigma 2pz orbit is found to be less than, it is found to be less than, it is found to be less than the energy and less than those of pi 2px and pi 2py. Okay, in case of O2 and F2, the molecule O2 and F2 molecule, the energy of this sigma 2pz is found to be less than those of this 2px and 2py, right? Why it is happening? This is due to the large energy difference between the 2s and 2pz atomic orbital, okay, in oxygen and fluorine. Why the energy of this 2pz is less than 2px and 2py? Because of the large energy difference between 2s and 2p atomic orbital in oxygen and fluorine. Now what will happen after that? Due to the large difference, these atomic orbital are unable to interact. Okay, so a lack of interaction, or we can say that interaction is here means that mixing. Okay, due to the large energy difference, this atomic orbital will not intermix. Okay, and the lack of these interactions means mixing tends to stabilize the resulting 2p sigma 2pz molecular orbital. Okay, this lack of interaction will tends to stabilize the resulting 2pz, resulting sigma 2pz, this one sigma 2pz molecular orbital. Okay, now that is why we are seeing that the sigma 2pz, this one, is of lower energy as compared to that 2px and 2py, right? So I hope you have understood this. Now in case of, if you are taking the case of lithium, beryllium, carbon, nitrogen, in this case also the 2s and 2pz orbital can interact due to the low energy difference between them. Okay, and the mixing of this 2s and 2pz or atomic orbital tends to destabilize the resulting 2pz molecular orbital. Okay, now that is why we will see that at that time, in case of this lithium, beryllium, boron, and that in that case we will see that the sigma 2pz orbit, this one, is higher energy as compared to that of the 2px and 2py molecule orbit, right, in Li2, Be2, B2, C2 and N2 molecules, right? So for O2 and F2 molecules, when we will see, I hope you have understood this, right? In case of lithium, beryllium, boron, carbon and nitrogen, right, the 2s orbit, the 2s and 2pz orbit can interact due to the low energy. These two will interact, means they will intermix due to the low energy difference between them. Okay, and the mixing of these 2s and 2pz atomic orbital tends to destabilize the resulting 2pz. It will, what it will do, it will destabilize the resulting 2pz, okay, molecular orbital. Now that is why what will happen, the sigma, this one 2pz, will have will possess a greater energy as compared to that of the pi 2px and pi 2py molecular orbital. Okay, so in case of lithium, beryllium, boron and carbon molecules, it will follow the same sequence. Now for the energy sequence for molecule O2 and F2, it will be like this. First will be sigma 1s, okay, after that sigma star 1s, okay, after that sigma 2s, after that sigma star 2s, okay, after that, as I have already told you, sigma 2px, after that it will be pi 2px and pi 2py, okay, and after that it will be pi star 2px, after that pi star 2py, and at last sigma star 2pz. So I hope you have understood this, how the relative order of energy of molecular orbital used to vary, right? So now at last we will see the energy level diagram, okay, molecular orbital diagram, which is called. So for your exam point of view, there are two important, which is N2 and O2 is very important. This one which is given here, so we will discuss here from here only. Okay, so as we know that the four diatomic homonuclear molecules such as Li2, Bu2, B2, C2 and N2, where energy difference is between 2s and 2p orbital is large, and hence they cannot interact, right? Just now we have seen that, right? So in that case, it will follow, the energy sequence will follow this order, right? This order, as you can see, as I have already written. So for N2 molecules, for N2 molecular orbital diagram, what we can see, suppose this one is, and this one is, when they will come closer to each other, they will form two type of bond. Either they will be bonding molecular orbital, or either they will be anti-bonding molecular orbital, right? So when bonding molecular orbital will have a lower energy than that of the anti-bonding molecular orbital, as you can see, right? Now next it will be, next when we talk about the 2s and 2s, when 2s and 2s orbital will come close to each other, they will form what again? Sigma 2s and sigma star 2s, as you can see. But the energy of this one, sigma and this sigma star 1s, will be will have less energy than this, right? As you can see here. Now next, after that, when 2p and 2p will come closer to each other, so at that time, see here carefully, when 2p and 2p are coming closer to each other, they are forming a two sequence. Either they will form, here you can see, sigma star, say pi star 2px and 2py, okay, and here pi star sigma star 2pz, and here again, as you can see, sigma star 2pz, and here pi star 2pz 2px, and here pi star 2pz, right, 2py, right? So this in this way we have to feel, right? So for this atom, for this homodiatomic molecules such as O2, F2 and N2, where the difference in energy between 2s and 2p orbital is small, and hence they can interact, and the energy diagram will be this, will follow this order. Okay, so I hope you have understood this, right? So let me explain it clearly. So once again we will see here. So when we talk about the N2 molecules, N2 type of molecules, so this is what it is, a nitrogen molecules, right? And it will be formed by the combination of two nitrogen atom, right? As you can see, because it is N2 is here, so it will form by the combination of two nitrogen atom. Okay, so what will happen, the nitrogen atom possesses a total 7 electron, right? And has an electronic configuration of what, 1s2 2px1, 2py1 and 2pz1, right? We'll have a electronic configuration of, let me write here, it will have an electronic configuration of 1s2, 2s2, 2px1 and 2py1 and 2pz1, right? So thus what will happen, there are 14 electrons in N2 molecules, right? Because 7 this and 7 of that one, so it will be 14, right? 7 from each. Now among this 14 electron, 4 are in a K shell, right? Among this 14 electron, 4 are in the K shell, that is 1s subshell, this one, and the one will be like the same for 2s, 2p x1, 2p y1 and 2p z1, right? So this one and this one, this one is and this one is, it will be in the K shell, which is called first one, first subshell, right? So it is assumed that this shell do not enter into the net bonding, and therefore it is called what, non-bonding orbitals. Since this one is and this one is K shell one, it is assumed that this shell do not enter into the net bonding, and therefore it is what, it is called what, net bonding, non-bonding orbitals. Now and the electron present in the non-bonding electrons. So listen carefully, among these 14 electron, 4 are in a K shell, right? So this is 1s subshell. So it is assumed that this shell do not enter into net bonding, okay, and therefore non-bonding orbitals, and the electron present in them are called non-bonding electrons, okay. Now does the nitrogen possess how many electrons? Then it will possess only 10 bonding electrons, right? Because this 4 has been eliminated from here, right? This 4 has been eliminated from here. Now so when these two nitrogen atoms combine together, at that time what will happen, their atomic orbital overlap to form a bonding and anti-bonding molecular orbital, right? So as we have seen before also, as we can see here, right? In this case, let me turn it down here so that you can see clearly. So as you can see here, right? So when these two nitrogen atom will combine, their atomic orbitals overlap to form what, bonding and anti-bonding molecular orbital, right? So as you can see here in this case, right? So on filling this orbital in accordance to the rule as discussed earlier, we have discussed, right? So we will get the following molecular orbital electronic configuration of two molecules, which will be sigma 2s square, sigma star 2s square, okay. After that pi 2px square, okay, pi 2py, let me write here. So when you will see, we will get the following molecular orbital electronic configuration for N2 molecules. It will be, I hope you have seen this, right? So it will be like this. For N2 it will be kk for K shell, first one. After that sigma 2s square. After that sigma star 2s square. After that pi 2px square. After that pi 2py square, and after that sigma 2pz square, right? So where this kk, what it kk here denotes the K shell electron, which is 1s square and 2s square, right? So from this molecular orbital diagram of N2, what we have seen here, this one, from the molecular orbital diagram of this N2, this is a molecular orbital diagram of N2. It became clear that these molecules contain 8 electrons in the bonding and 2 in the anti-bonding molecular orbital, right? So that is what we can say, NB will be 8 and Na will be 2, right? Means what? Since what we have seen that here, it is clear that this molecules contains 8 electrons in the bonding, okay, and two electrons in the anti-bonding side. So what we can write, in bonding it is containing 8 electrons, so it we can write Nb is equal to 8, and in the non-bonding, in anti-bonding, it is containing 2, so we can write Na is equal to 2, right? So now if we are asked to find out the bond order, so bond order we can find out like this. We know that Nb minus Na by 2, which will be 8 minus 2 by 2, which will be 3, right? So I hope you have understood this, the formation of anti-molecule. Now from the value of this bond order and the molecular orbital diagram, we can conclude that the bond order value equal to 3, which suggests that the two nitrogen atoms are linked together by a triple bond, which is N 1 2 3 N, right? Triple bond. Now when we talk about the stability, the bond order is positive, okay, and the high value, and has a high value which is equal to 3, as we have got this, right? Now the value of since the value is the highest of all the non homonuclear diatomic molecules, okay, this value which we have got here 3, this value is highest of all the non homonuclear diatomic molecules, right? So what we can say, this N2 molecule should be very stable and possess and should possess a very high value of bond dissociation energy, okay? So this from this predict we can predict that or we can agree what we can say, that these N2 molecules will have a will have or will be very stable, right? Now here N2 molecule has been found to be very stable, so its bond dissociation energy is found to be, when you will see the bond dissociation energy, it will be something like 945.4 kilojoule per mole, which is quite high, okay? Now again we will talk about the diatomic nature. So N2 molecule possess all the electron pair, okay, right? And you will see here all the electrons are in pair, right? As you can see, all the electrons are in pair, here also. So since the all it N2 molecule possess all the electrons paired, hence what we can say, it should have a diatomic nature, okay? Paired electron means diatomic in nature, okay? And this prediction is also, or we can say, yes, this they are diatomic in nature because they have paired electrons, right? So I hope you have understood this about the MOT of molecular orbital diagram of nitrogen molecule type, right? Now next is oxygen. So when we talk about the oxygen, so as you can see 1 2 3 and 4, 1 2, this one we will leave because this is 1s, we will not count, this is in K shell. So it will form 4 bonding and 4 anti-bonding molecular orbital. Let me show here. This one is 1 2 3 and 4, and here anti-bonding is 1 2 3 and 4, right? So it will form 4 bonding and 4 anti-bonding molecular orbital. Now it should be noted that the auto molecules, in auto molecules, the 2pz, sigma 2pz, this one sigma 2pz, this one sigma 2pz orbit lies between 2px and 2py, right? It lies between 2px and 2px and sorry, sigma 2px and 2py, sigma 2px and sorry, it lies between pi 2px and pi 2py, right? So as we have discussed also about this, right? So on filling the 12 bonding electrons in this molecular orbital in accordance to the role, as we have discussed earlier, we will get a molecular orbital diagram of two O2 molecule, as we can see here, right? How we have filled this will be a non-bonding because 1s. So first we will 1 2 here, 2 here, after that 2 here, 2 here, 2 here, and what is left, 2 is left here, so this one will be 1 here and another one will be here, right? So when we will see the orbital electronic configuration of O2 molecules, which can be written as follow, that is again in case of we have seen, right, O2. So first will be kk here is what, it is a closed k shell representing 1s by sigma 1s square and sigma star 1s square, right? So after that it will be sigma 2s square sigma star 2s square, after that sigma 2p z square 2p z square, after that pi 2p x square, after that pi 2p y square, after that pi star 2p x 1, and in the last pi star 2p y 1, right? So this will be the electronic configuration. Okay, so as you can see how it has, this is the uh, molecular orbital diagram of O2, right? Now next is, here you can see, here is two unpaired electron, right? This one and this one, there are two unpaired electrons. So I will tell you what is the role of this unpaired electron. So as we have seen, right, everything. So now from this diagram or molecular orbital diagram of O2 molecules, we can conclude that the oxygen molecules contain 8 electrons in the bonding and 4 in non-bonding, right? So 8 electron in bonding, as you can see, 2 to 4 and 2, 8 electron in bonding, 2 4 6 and 8, right? And 4 electron in anti-bonding, which is this one, 2 3 and 4, right? So 4 electron in anti-bonding. So what will be the bond order? So bond order will be 8 minus 4 divided by 2, which is will be 2. As you can see here, bond order is 2, right? So on the basis of this molecular orbital diagram and the value of this bond order, we can conclude that the status of the bond, when we talk about the status of the bond, since the value of the bond order is 2, right, bond order is 2, as you can see. So what we can say, the oxygen atom in an O2 molecule should be linked together by a double bond, okay? And the these predictions agree well with the experimental facts also, right? Now again, when we talk about the stability, so the positive and high value of bond order suggest that the O2 molecule should be quite stable, okay? And this prediction is again in an agreement with the observed fact, as we have seen here, right? Now when we talk about the stability of this O2 molecule is confirmed by the high bond dissociation energy, which will be equal to something like 498.7 kilojoule per mole, 498.7 kilojoule per mole, right? So now as we have seen here, what I have told you, there are two unpaired electrons is there, right? As you can see, having a two unpaired electron. So since they have two unpaired electrons, they are called paramagnetic in nature, right? So paramagnetism of O2 molecules, when we can confirm like this, that from this molecular orbital diagram we have seen that the Aufbau order, when we talk about the Aufbau order of filling a molecular orbital, leaves two unpaired electrons, right? This leaves two unpaired electrons, and one each in pi 2x, as you can see, pi star 2x and pi star 2y molecular orbital. So thus what we can say, that oxygen atom possesses two unpaired electrons even in a ground state. So the unpaired electrons impact what? Paramagnetic character of the oxygen molecules. So thus we can say that the oxygen molecule should be paramagnetic in nature, right? So I hope you have understood this. Now when we see the experimental measures of paramagnetism of O2, it confirms the paramagnetic predicted by the molecular orbital theory, right? And this is a big success for the molecular orbital theory. So I hope you have understood this, right? So this was all about your molecular orbital diagram and molecular orbital theory. So some more are given here, as you can see. You go and study at home. If you can't, you can contact me, okay? So this was all about the molecular orbital theory and molecular orbital diagram. Now next one is hydrogen bonding. So about hydrogen bonding and dipole moment, this one is dipole moment and resonance. We will discuss about this in the next class. Okay, so I hope today's class you have understood. So keep up to this. In the next class we will start with the hydrogen bonding. Okay, so till that, thank you and have a nice day.